Hey, Flip Geometry, how you doing? This is kind of a weird section. We have been working this whole time on direct deductive proofs. Start with something, prove your way to something else. This lesson shows you that you can prove something by proving that the alternative is not true. This only works if you have something where it's a digital option. Either this is true or it's not. And if proving that something is true is frustrating to you, sometimes it's better to say, oh, well, if this is not true, then this has to be true, and prove that this isn't. And then you can say the opposite then must be the case, that the first condition was true. You won't use this a whole lot. So if this throws you for a loop, it's okay. Grin and bear it, bear down, push through. We'll get through it together, and you won't have to do this a whole bunch. But it is an interesting skill to have in your bag for the future. Okay, so this is indirect proofs. An indirect reasoning or an indirect proof shows that any alternative to the stated conclusion is false. And so therefore the original statement must be true. Okay? So you're proving the alternative's false to prove what you want to prove true as true. In most indirect proofs, the statement and its negation are the only possibilities. This is a digital thing, a yes, no, a 1, 0. This is either a scalene triangle or it isn't. This is either a congruent triangle or it isn't. This is either an equilateral triangle or it isn't, right? Yes or no, two option situations. You wouldn't use this for something that has multiple options because then you'd have to negate all of the other options except the one that you're trying to prove true. And in that case, it'd be a lot easier just to prove the one thing true, right? Here we go. Something that we're going to be needing to review is the relationship between a contrapositive and a conditional statement. Conditional statement, if P, then Q. The contrapositive, you reverse the order and you negate them both, right? So now you have not if P, then Q, but if not Q, then not P. And we're going to give you a couple of examples to demonstrate that conditionals and their contrapositives have the same truth value. You already know that, but I'm going to give you a quick example to show that to you. Let me just remind you of how this works. So we're going to look at the contrapositive of a statement and the truth value of the original condition and the truth value of the contrapositive. So if a triangle is isosceles, then its base angles are equal. We know that that's true. What's the contrapositive of that? Well, if its base angles are not equal, then it's not an isosceles triangle, right? I switched the hypothesis and the conclusion, and I negated them both. So this was the conclusion. This was the hypothesis. I put them in opposite order and I negate them both. If base angles are not equal, then it is not an isosceles triangle. That's the contrapositive. Part B, what's the truth value of the initial conditional? We know that that's true. That's one of our theorems. Okay? And if we think about this, this is also true. If an isosceles has equal base angles, then if the base angles aren't equal, it's not an isosceles triangle, right? So the contrapositive is also true. No matter how many times you poke at this, you're going to get the same answer. Contrapositives have the same truth value as the initial conditional. Another review, we've already talked about modus ponens and modus tollens, and when we introduced them, I said don't stress out too much about the vocabulary. You're going to use these enough without stressing about their vocabulary. Well, the vocabulary comes up a couple more times. This is one of the lessons, but it's not a big deal. Here we go. If you live in Virginia, you are a U.S. resident. That's the conditional. You can use the modus ponens to then say, well, if I have the hypothesis, then I have the conclusion, right? So Janice lives in Virginia. Therefore, she's a U.S. resident, right? That's the modus ponens. It's a conditional statement. I have the hypothesis, therefore I also have the conclusion. Modus tollens negates the conclusion. If you live in Virginia, you're a U.S. resident. But Neil is not a U.S. resident. Therefore, Neil does not live in Virginia, right? And here's a little happy picture to show where Janice and Neil are related to each other. Virginia residents are part of U.S. residents. Janice is a part of Virginia, so she is a part of the United States. Neil, however, is not a part of the United States. He lives in Quebec. Quebec is not a part of the United States. It's also not part of Virginia, right? So we can conclude that since Neil is not a resident of the United States, he's definitely not a resident of Virginia. And so that's just an example of modus tollens and modus ponens. You've seen them before. They're just coming back and waving at you again. So how do you do these indirect proofs? Well, you're going to be given a statement, some givens, and you're going to be given what you need to prove. And then you're going to start with assuming the negation. Okay? So before, you've started with the givens and walked towards the proof, the conclusion statement. Now you're going to say, oh, you want me to go there? Instead, I'm going to go over here. And you're going to walk as far down the logical road as you can, assuming the opposite is true until you run into a brick wall. And you're going to say, oh, can't do that. And therefore, this is not the road that takes you to the answer, right? Assume the opposite. Use assumptions to reasonably deduce a contradiction of a given information. So you go until you contradict your given or a known fact, definition, etc. And then you say, oh, consequently, this can't work, right? And so that is where you get back to the statement that you were trying to prove in the first place, because you proved that the alternative is false. Let me give you a quick example. Before I give you that quick example, let's look at the law of contradiction. If an assumption leads to a contradiction, to something that is not true, then the assumption is false, and its opposite, its negation, is true, right? So we're going to assume the opposite. We're going to walk down that road till we hit a wall, and we're going to say, oh, see, this doesn't work. This is what I should have done, right? That's the law of contradiction. Here's an example. You're going to write an indirect proof showing that if x equals 4, then 3x plus 7 is not 22. So I have this statement, 3x plus 7 equals 22, and I am going to go where it tells me to. 3x then it equals 15, right? I'm solving for x. X equals 5, and I said, oh no, but x equals 4. I have a contradiction, and so therefore 3x plus 7 is not 22. This is what I was told was true. I assumed that the opposite, C equals instead of not equals, was true, and then I show that I have a contradiction, and therefore the original statement is the one that's true. Let's look at one real quick with geometry. If I have this triangle that is stated to be scalene, and I'm also told that BD is not a perpendicular bisector of AC, I want to prove that. So I'm going to assume that BD is a perpendicular bisector of AC. Then I'm going to show that, well, if that's true, then I have a right triangle and a right triangle, and BD is itself, and DA and DC must be congruent if it's a perpendicular bisector. So I have leg, which means that these triangles must be congruent, which means corresponding parts of congruent triangles are congruent. So BC has to be the same thing as AB, which means that this is an isosceles triangle. And then I say, oh wait, just kidding, because I was told that this was a scalene triangle. But I just proved that it's an isosceles triangle if BD is a perpendicular bisector. It can't therefore be both scalene and isosceles, so therefore BD is not a perpendicular bisector. All right, that's the kind of stuff you're going to be doing. I'm going to hold your hand through it. It's going to be great. We're going to survive, and Jesus will be worshipped at the end. Let me know what questions you have in class when I see you tomorrow. Otherwise, I will look for them in the comments field and get to them as quickly as I can. Until then, God bless you. Jesus loves you, and so do I. Good night.